Most stars die a quiet death, but massive stars typically die in spectacular supernova explosions. Left behind are astounding objects of incredible density.
A supernova is the last gasp of a star's evolution when in the core of the star it runs out of hydrogen gas, the star basically collapses and has this extraordinarily violent explosion. We believe, theoretically at least, leaving behind an extremely compact object with a mass comparable to that of the sun that can be spinning extremely rapidly. It'll be an object maybe only 10 or 20 miles in diameter.
In the context of the death of massive stars, we still don't understand the physical process that ejects the outer envelope. We know the core is left behind as a neutron star because we see it.
What we know of such exotic celestial bodies as neutron stars, pulsars, and black holes began with a single event, witnessed almost 1,000 years ago.
The ancient Chinese kept a very close watch on the sky because they felt that astronomical phenomena had sociological significance. In other words, they were astrologers. And on July 4, 1054, the then court astronomer recorded the appearance of what they called a guest star, blazing out in a part of the sky that we now call the constellation Taurus. He said that it was visible by day like Venus for about 2 weeks, and after more than a year, it gradually became invisible. That's a very impressive blaze, something that's visible by day like Venus. And for a star to take as long as more than a year to fade below naked eye visibility is also very impressive.
The remnant material, the cloud of gas that was sent out into space, was actually observed again when the telescope was invented. In the 19th century, for instance, Lord Rosse, a very wealthy British nobleman, built himself a large telescope with which he observed all sorts of things in the heavens. Among other things, he observed a cloud of gas which he called the Crab Nebula.
The Crab Nebula, which has been known for a couple of hundred years as an astronomical object, is called the Crab Nebula because the nebulous filaments that are luminous that one sees through a telescope resemble that of a crab. And from astronomical observations of this nebula, you can see that it's expanding. You can see the gas is moving out. You can measure the velocities of that gas.
And you can take images of it exposed a few decades apart, compare them, and measure the rate at which the nebula is expanding. That was actually my PhD dissertation. It was called Motions and Structure of the Filamentary Envelope of the Crab Nebula. Not that such measurements hadn't been made before, but these were genuinely better because by the time I did my thesis, we had 20 years of plates from the 200-inch telescope.
The cloud of gas was expanding. And if you extrapolated back in time to find out when that expansion had started, it came out that the gas had been expanding for about 1,000 years, which meant that whatever had caused the cloud to expand had occurred around the year 1054 or so. It wasn't long before astronomers identified this object as the remnant of the 1054 explosion.
In 1933, Fritz Zwicky, a Swiss-American astronomer, and Walter Baade, a German-American astronomer, suggested that the supernova phenomenon was the result of a collapse of a normal star to a neutron star. They recognized that the Crab Nebula had been one of those. They suggested that the event of 1572, seen by Tycho, and the event of 1604, seen by Kepler, were supernovae, along with about 5 or 6 events in other galaxies that 20th century astronomers had studied.
The neutron stars are called neutron stars because we believe that they're primarily made out of neutrons, which are components of the atomic nucleus. And in fact, the density of a neutron star is very close to the density of the nucleus of the atom. This is the most dense material known in the universe.
So, while less massive stars eventually collapse into white dwarfs, supported by the pressure of their own electrons, high-mass stars overcome that pressure to collapse at their cores into neutron stars. In 1930, S. Chandrasekhar, a 19-year-old student, calculated that for such stars to form, they must have a critical amount of mass, now known as the Chandrasekhar mass limit.
We believe that all neutron stars are formed when the Chandrasekhar mass is achieved. That can happen in the core of a massive star, more massive than perhaps 8 solar masses, or it can happen in a binary where the star, one star, is dumping mass onto a white dwarf that thereby achieves the Chandrasekhar mass and collapses.
And what happens is that when the electrons become sufficiently energetic, it becomes energetically favorable for them to merge with protons to make neutrons and release neutrinos. It's called inverse beta decay. And the product neutron is a much more massive particle than the electron. The result is it can be crammed in a much smaller box.
But the dense neutron star at the center, which had been left over by the explosion, was still unseen. And astronomers, in fact, didn't expect to see it. A ball of gas only 14 miles in diameter has to be impossibly hot to produce enough light to be seen from the Earth. And so astronomers didn't believe it could be that hot and didn't believe that they would ever see it.
With no hopes of ever observing a neutron star, astronomers did not actively seek them. Their eventual discovery came as a total surprise.
In 1967, a British graduate student named Jocelyn Bell was carrying out her thesis research with a telescope which was designed to observe radio waves from space. And she noted on the records of the telescope regular pulses of radio waves coming from a particular spot in the sky. They recurred every night at the same spot. She thought for a while about them and couldn't understand where these regular pulses were coming from. There were no known sources of radio waves that produce signals so well defined and so regular in their occurrence. And so for a while, she and her thesis advisors thought that perhaps they had detected the first signal from an extraterrestrial civilization. They called the source the LGM because they thought it might be coming from little green men. When they discovered a second and a third and then a fourth source, like the first, coming from different spots in the sky and pulsing at different rates, it became clear that they were looking at something natural, but they didn't quite understand what it was. They published their results, and astronomers called these new radio sources pulsars, for pulsating radio sources.
With a little bit of thought, they recognized that these extraordinarily periodic phenomena were most reasonably explained as being due to the rotation of some astronomical object. And on theoretical grounds, people soon realized that these objects were likely supernova remnants, so-called neutron stars, the burned out core of an exploding star.
Well, the exterior of a neutron star is dominated by its very intense magnetic field. And this intense magnetic field, as it rotates, appears to generate streams of charged particles, probably electrons and positrons. And what we see typically is the radio waves emitted by these streams of charged particles. These radio waves appear to be emitted rather like a lighthouse beam. And much as when we see a lighthouse from a distance, it seems like the light is flashing at us, in fact, the lighthouse beam is continuous and it's rotating and illuminates all of the region around it, but at different times.
Some supernova explosions leave behind neutron stars, and as those neutron stars spin and produce beams of radiation, if those beams of radiation don't sweep over the Earth, then we'll never see that neutron star. So that supernova remnant will look empty. So we shouldn't be concerned that most supernova remnants don't contain pulsars. On the other hand, we see lots of pulsars that don't have supernova remnants around them. That shouldn't worry us either, because pulsars, spinning neutron stars, can be active and remain luminous for ages of a million years or more. But a supernova remnant is really very ephemeral, and it's mixed into the interstellar medium within a few tens of thousands of years. It's gone within 50,000 years. So most pulsars that we see produced by supernova explosions have long since lost any supernova remnant that might have been around them.
To confirm the hypothesis that pulsars are indeed rapidly spinning neutron stars, astronomers knew they must find one in the center of a supernova remnant.
It was known that the Crab Nebula was a supernova remnant, and so it was an excellent place to look for a possible pulsar. It was promptly seen, and because it's so young, only 1,000 years old or so, people decided to look in other places than in radio wavelengths, and actually look there with optical telescopes to see if they could find an optical pulsar.
I think the most exciting observation that I have ever made personally was of the pulsar in the Crab Nebula. The Crab Nebula is the result of the supernova explosion, which was observed in 1054 AD, and it was discovered in the late 60s that there was a radio source that was beeping 30 times a second in the center of the Crab Nebula. Working with my colleague Joe Wampler, we devised a system that allowed us to take a picture of the center of the Crab Nebula with a spinning disk that allowed it to work like a strobe light and freeze the rapid flickering of this pulsar. And we saw right in front of our eyes on the TV screen this pulsar just pulsing away at us. And it was a very exciting moment, because instantly we knew which object in the Crab Nebula was the pulsar, which star, and that in fact it was pulsing in the optical just as it was in the radio. And it was such a graphic, immediate demonstration of some scientific result that it was extraordinarily exciting.
At the time, the Crab pulsar was also unique, and really I think had the most fascination to us at the time, because it was far and away the fastest known pulsar. Most pulsars were rotating with periods of a few seconds to a few tenths of a second. Here was something that rotated 30 times a second. Since then, amazingly enough, people have found pulsars that pulse up to about 1,000 times a second.
A number of people have tried to calculate the upper limit to the mass of a stable neutron star. The result is that the upper limit is still somewhat uncertain. It's certainly larger than the Chandrasekhar mass, or we wouldn't see neutron stars. It's certainly not larger than about 3 solar masses, because a 3 solar mass neutron star would have a speed of sound exceeding the speed of light at its core. And we don't really like the idea of speeds of sound that exceed the speed of light. Probably the best bet is an upper limit somewhere around 2 or maybe 2.5 solar masses. That means that if you have a very massive star whose core collapses to make a supernova, and the collapsing core is more than 2 or 2.5 solar masses, or if you have a neutron star and you drizzle enough material on it and drive it above that limit, further collapse occurs. It's so compact that the escape velocity from its surface is larger than the speed of light. You have what's called a black hole.
A black hole is one of the strangest stellar remnants that we can possibly imagine. How does a black hole form? You take a star, a very large star. When it finally finishes its life cycle, it gets so small, compresses down to such a small size that nothing can get away from it, not even light. And once an object has compressed so much that nothing can get away from it, not even light, we call it a black hole. Why? Because you can't go faster than the speed of light. So if you get too close to it, abandon hope, all ye who enter here. You get too close to a black hole and you aren't going to come out again.
It is quite probable that the formation of a black hole from an extremely massive star need not be preceded by an observable supernova event. If the iron core that begins to collapse is too massive, and if too much material follows the collapse and does not rebound with sufficient energy, then the rebound essentially stalls, it can go out part way, but gravity will eventually take over and suck the material back in. This will give rise to the formation of a black hole without producing an observable supernova. And indeed, theoretical calculations of supernovae have a difficult time producing successful explosions. What one generally gets in the computer calculations are black holes, not successful supernovae. So it could well be that a substantial fraction of the most extremely massive stars never become supernovae, but go directly to the black hole stage.
When a black hole is formed from a dying star, the boundary, the event horizon that it creates is only 10 or 12 miles from the center. A black hole is a very tiny object, and a black hole attracts matter to it only due to gravity. Black holes are not vacuum cleaners in space. They don't go around sucking things up with more power or other effects besides their gravitational force.
We are not entirely certain, based on the observations, that black holes even exist. I would say that the observations lead us to conclude with greater than 99% certainty that black holes exist and are the remnants of extremely massive stars, but we have never actually witnessed the formation of a black hole.
So astronomers began searching for the elusive black hole. But among the brilliant stars of the galaxy, how could they detect a relatively tiny object that emits no light?
From an astrophysical point of view, the important thing about a black hole is its mass, its angular momentum, and the fact that it really is very compact. That does have observational consequences. In particular, you can have a black hole in a binary system, and it will exert exactly the same force on the companion star as a normal star of the black hole's mass, and the normal star will be seen to be going in orbit around something that is not a source of visible light. And this was predicted as the right way to find black holes, as well as neutron stars.
If a black hole, for example, is in a binary star system, then the black hole will pull matter from its companion into itself. However, a black hole is typically 10 miles across or so. It's very small. And therefore, when it pulls the matter from the other star onto it, that matter can't all fall in at once. The matter from the companion has to wait its turn, just like water going down a drain. So as the matter from the companion swirls round and round and round the black hole waiting to go down into it, other matter from the companion star is pouring onto this region. There is created a disk around the black hole called the accretion disk of matter waiting to get in.
But when it goes down the tubes, it gets very hot. And so in the process of disappearing, it radiates X-rays. And you recognize a black hole binary because it's an X-ray source, so you know there's something compact there, and the mass of the X-ray object is too big for a stable neutron star.
If the X-rays are emitted by the gas before the gas enters the black hole, before it crosses the event horizon, then those X-rays can escape. So if we look at a list of objects that are producing X-rays, some of those objects might be black holes swallowing matter, and so that's a way to search for black holes.
Probably the most likely black hole candidate is in the constellation Cygnus, the Swan, and it's called Cygnus X1, meaning it's the first X-ray source that was discovered in Cygnus.
The one in Cygnus turned out to be a binary star, and when the optical identification was made, many astronomers did spectra and found that indeed it was a binary star with a period of about 6 days, and that the velocity amplitude was so large that the mass of the companion object was at least 3 or 4 solar masses and probably 6 to 10. In other words, it was in the black hole class, not in the neutron star class. And Cygnus X1 is still the best established of the black hole X-ray binaries. There are now 3 or 4, maybe 5 or 6 other systems for which you can say it's compact and therefore it must be a neutron star or a black hole, but it's too massive to be a neutron star, therefore it's a black hole.
Even though evidence of incredibly compact objects can be observed, their theoretical implications defy imagination.
A black hole is an object predicted to exist by Einstein's general relativity theory. An object which is made out of the fabric of curved space-time. It's not made out of matter. It's not made out of electrical or magnetic fields. It's made out of pure curved space-time and nothing else. We have special solutions of Einstein's equations that describe black holes. The first such solution was found by Carl Schwarzschild in 1916. It describes a black hole that is not spinning. The second was found by Roy Kerr in 1963. It describes a black hole that is spinning.
Most black holes are believed to be rotating Kerr black holes rather than the non-rotating Schwarzschild black holes, because all the stars that we have examined in detail are known to be rotating. The sun rotates about once a month, and the other stars in our galaxy and in the universe are believed to be just like it in their behavior, rotating, and therefore when some of them do form into black holes, the black holes that they create will also be rotating.
At the core of a black hole lies a singularity, pure space-time. Surrounding that, at a finite distance, the Schwarzschild event horizon. And if the black hole is spinning, a region known as the ergosphere.
It seems completely clear from the study of Einstein's equations of physics that inside a black hole there is a singularity. The singularity is a region where the pull of gravity is so strong, or to say it differently, the curvature of space, the warpage of space-time is so strong, that anything which falls into the singularity will get destroyed.
Nobody's ever seen a singularity. Nobody's ever going to see a singularity. They do not occur naked in the real universe. They're always hidden inside the Schwarzschild horizon.
It's called the horizon because it is the boundary beyond which you cannot see anything. If you're up near the black hole and you try to look at something that is falling into the black hole, you cannot see it once it passes the horizon. You can't see it once it passes the horizon because the light that it emits to you, by which you would see it, itself gets pulled back into the black hole once this object has moved inside the horizon.
Outside the event horizon, where the space is being dragged around by the rotation of the singularity inside the black hole, out to twice that distance is a region called the ergo region. Inside the ergo region, you can travel around and get away from the black hole if you are moving fast enough. If you're just falling inward, you'll spiral into the black hole and pass through the event horizon, and that's that.
The speculation that one might be able to go inside a black hole through and re-emerge somewhere else in the universe or in the distant past, that speculation was actually based on an exact solution of Einstein's equations of general relativity that describes such a thing. However, despite that basis in Einstein's equations, no theoretical physicist believes that this is possible.
Unfortunately, when you talk about real black holes, it does not appear possible to be able to do it. So not even the pieces of the spaceship would survive. And it's also true that as you get too close to a black hole that you make from a star, you get about 1,000 miles away from it, and the tidal gravitational forces are going to do very strange things to people. If you imagine yourself falling feet first, you're going to get stretched out because your feet are closer to the black hole than your head is, so they're going to tend to be pulled towards it faster. But you're also going to get squished together because your two shoulders are going to fall towards the hole on converging paths. So we can find these kind of torture instruments in the dungeons of places like the Tower of London. They had the rack and the straitjacket, and in a black hole you get put in the rack and the straitjacket at the same time. So for most realistic black holes you would have spaceship parts and astronaut parts. No, I don't want to go exploring a black hole that way.
One of the interesting questions about black holes, which is unanswered, is do they emit gravitational radiation, especially when they spiral or collide with each other? We are developing the technology to look for that radiation from colliding black holes.
It's radiation that consists itself of ripples of warpage of space-time that leave the vicinity of the black hole, that travel out through the universe, getting ever weaker as they travel out through the universe, then pass through the Earth. And if we can catch these ripples and study the curvature in them in detail, we should be able, from those ripples, to infer the detailed map of the curvature of space around the black hole. This, then, is one of the challenges of a new field of astronomy called gravitational wave astronomy that is likely to blossom within the next decade or two.
There are people who feel that when you have the right theory of gravity, there will be no singularities. There will never be a case of stars collapsing to zero radius, that the correct theory of gravity will not predict these strange phenomena. Whether the right theory of gravity will still do that or not, I make no promises.
The death of massive stars marks the beginning of the strangest of celestial objects: neutron stars, pulsars, and black holes. Our quest to understand these objects challenges current laws of physics and pushes the frontiers of astronomy.